Hello everyone, you're welcome to this channel once again. Today we have another question from natural frequency of a mass system. Now let's read through the question. Find the natural frequency in Hertz for the system illustrated in the following figure below. Assume the mass momentum of inertia of the pulley about the center equals I 5 times 10 raised to the power 10 raised to the power 5 kilogram per meter square, and the R, the radius of the pulley, is 10 meter, and the K equals 10 raised to the power 6 Newton per meter, and the mass M suspended on the pulley equals 150 kilogram. Now here we have a dynamic system of a pulley connected with a mass system and a spring system having a rotation of 2r theta, with the moment of inertia of the pulley equals 5 times 10 raised to the power 5 kilogram per meter square. Now, looking at the pulley system in a dynamics form, how do we approach this particular question? First of all, let's pull out our parameters. We're given the I, which is moment of inertia, 5 times 10 raised to the power 5. We're given the radius of the pulley, which is 10 meter. We're given the K, stiffness of the spring attached to the pulley, which is 10 raised to the power 6 Newton per meter. We're given the mass attached to the pulley, 150 kilogram. Now, don't let us forget that the distance of rotation of the pulley to the mass system and the spring equals x equals r theta. And if we have the first derivative of this, we have x dot equals r theta dot. And by squaring it up, we have s dot squared equals r squared theta dot squared. Now, our first approach is to first deduce the equation of the kinetic energy and the potential energy using Lagrange equation here. So therefore, our kinetic energy equals Ke equals T equals half of rotation of moment of inertia to the product of theta dot square plus half of mass of the body attached to the pulley to the product of x dot square. So that gives us this particular equation. Also, using the potential energy, which is given, is called half of K, that is the constant of the spring, to the product of s squared. That gives us half of K into 2 pi r theta dot square into bracket. That gives us 2k r multiplied by theta dot square. Now that we have found both the potential and the kinetic energy, now by using the Lagrange equation that say we should find the first derivative of the sum of kinetic energy and the potential energy together. So by finding the derivative of both kinetic energy and the potential energy, we can deduce that our delta t over dt equals delta t over d theta equals half of I plus mr squared into bracket theta dot square plus 2kr square. Theta dot square equals 0. So by finding the derivative of this particular equation, we can deduce that we have this equation I plus mr square into bracket theta dot plus 4kr square theta equals 0. Now that we have found the final equation of the Lagrange of this whole pulley system dynamics, we can now equate it to the standard mass system equation, which is ms dot dot plus cs dot plus ks equals 0. Now, by linearizing two of these equations together, we can deduce that our mass equals I plus mr square. And we can deduce that the k constant equals 4kr square. So we can now plug it into the natural frequency equation, which is Wn equals root of k over m. So that gives us this. And finally, our natural frequency, that is Wn, equals 27.87 radian per second. By finding the natural frequency of the whole pulley system, we can now convert it to Hertz by using Wn equals 2 pi f. So our f, that is the frequency in Hertz, equals Wn over 2 pi, and that gives us 27.87 over 2 multiplied by 3.14. And finally, our frequency in Hertz for this particular system equals 4.44 Hertz. Thank you very much.